Welcome back to Physics 142. We've been talking about magnetic fields and magnetic forces, and in this video I want to give an introduction to the concept of magnetic flux. And I want to do that by comparing to some properties from electricity and from electric fields that we know about, and see sort of how they contrast and compare with similar properties in magnetism. So the first thing I want to think about is I want to think about how magnetic field lines compare and contrast with electric field lines. So for electric field lines are these lines that connect the different electric field vectors, right? So if we had maybe, some sort of charge, right, and we could draw electric field lines, right, as lines that connect all the different vectors, right? Because if we picked this spot in space, we'd have a force vector like that, and this spot in space, a force vector would be smaller, right? And the electric field lines would connect all of these sort of electric field vectors, right? All the electric field vectors that are all going out in all the different directions, and the electric field lines connect them. An important point about electric fields, though, is that force is along electric field lines, right? The force is along electric field lines, right? So if we want to know what direction is the force, well, you just pick a spot on a electric field line, and you say, oh, hey, the force is in that direction, all right? For magnetism, though, again, if you take magnetic field and you think about magnetic field as a bunch of vectors, right? So here's magnetic field, it's a bunch of vectors. Magnetic field lines are just lines that connect all of those vectors, right? So we can draw magnetic fields with these magnetic field lines, and we've already been doing that. However, there's an important difference in thinking about magnetic field lines versus electric field lines, and that is that we know that forces, the force law for magnetism, involved the velocity of charges, QV, crossed with B, right? It had this cross product, and so that means that the force is always perpendicular to magnetic field lines, all right? So force is perpendicular to magnetic field lines. So here, if you want to know the direction of the force, it's not going to be along the line. It's always going to be perpendicular, and the exact direction is going to depend on the velocity that the particle is moving. So magnetic field lines don't show you the direction of force, while electric field lines do, right? Electric field lines show you the direction of force. Magnetic field lines show you something perpendicular to the direction of force. So that is an important difference to keep in mind. Now, one of the reasons that we're talking about electric field lines and magnetic field lines is that electric field lines were a way that we were able to conceptualize the idea of electric flux. Basically, for electric flux, what we would do is we thought about some area, maybe this is a window or something, right? It has some area A, and then we would think about the amount of electric field going through that area, right? We think about electric field going through that area, or we'd think about electric field lines going through that area. And one of the ways that we defined electric flux is we said it's just the number of field lines that go through that surface, right? If you have more field lines, that is, more electric field going through the surface, then you get more electric flux. So how does that look for magnetism, right? For magnetism, if I have, some window again, so here's my window, and it has some area A, and I want to know about magnetic flux, well, you might imagine that I could send some magnetic field lines through that window, right? So now I'm going to send some magnetic field lines through that window. And it turns out that actually we define magnetic flux the exact same way. We say it's, the number of magnetic field lines there that are going through that surface. If you have, more dense, more packed together magnetic field lines, that means you have more magnetic field. So it's however much magnetic field is passing through that surface. All right, so magnetic flux is, amount of magnetic field lines is field lines through surface. So while the relationship to force is a little different, our definition of flux is actually exactly the same. And so for electric flux, we use the symbol phi. All right, and now we'll maybe give that a subscript E to indicate its electric flux, right? And similarly for magnetic fields, we can use the same symbol. We say flux. The magnetic flux is, again, phi, but now we give it a subscript B to indicate that it's magnetic. And you might remember that for electric fields, the formula we had, phi, was the integral of E dot dA, right? What that said is if you have more electric field, you get more flux. If you have a bigger area, you get more flux. And the relative direction of the two mattered, right? If we thought about some area vector, right? If they were pointed in the same direction, then that meant a lot of flux, right? Otherwise, if we tipped this on its side, so the area vector was going up, well, then nothing goes through the window, and so you don't get any flux, right? Well, the same thing ends up being true for magnetic fields, all right? We end up defining it the same way. We say it's the integral, but rather than E, now we say B dot dA. All right, it's the integral of B dot dA, the amount of magnetic field going through the window, because again, if you have more B, you get more flux. If you have a larger area, you get more flux. And again, if we tipped this window on its side, right, it's the relative direction of the window or of the area, the bit of area, and the magnetic field matter, right? There would be our area vector, right, would be pointed that direction. Oh, excuse me, sorry. If they're pointed the same way, then, right, that is the magnetic field passing through the surface, then you get a lot of flux, right? If I tip this on its side, then you would get no flux. And just to remember, right, how dot products work, we could also write this then. A dot product is the magnitude of B times the magnitude of A times the cosine of the angle between them, right? And I'll use theta here as the angle between the area vector and the B vector. So magnetic flux is a useful concept, right? Electric flux was a useful concept, and part of the reason electric flux was a useful concept is that it led us to Gauss's law. And so we might remember that for electric fields, Gauss's law looked like this. It said that that amount of flux going through a closed surface, right? If we thought about some closed surface and the flux through a closed surface, right? So what does a closed surface look like, right? Well, I think we use like bag of potato chips or something, right? Something that's a closed surface. We realized that that depended on the amount of charge that we enclosed in the surface divided by epsilon naught, right? That the flux going through the surface, if you put more charges in it, if you put a bunch of charges in it, then you ended up with more net flux through that surface, right? As opposed to just a field line that just passed through, some charge out here, it doesn't actually contribute to the net flux because what goes in also comes out. So how does this work for magnetic fields? All right, let's think about having some surface for magnetic fields, right? And we think about magnetic field lines, right? Well, any magnetic field line that starts on the outside and goes through, well, that's not going to contribute any. So the way that we need to, make some flux in here is we would need to have a sort of magnetic charge. Except we have the problem that there aren't any magnetic monopoles. We've never observed any magnetic monopoles. So if we write the flux over a closed surface of B dot dA, all right, well, the thing about magnetic field lines is they're always loops, right? They always keep going. They're continuous, right? They never end. So they never come to a spot. You can never have a source of magnetic field inside a surface because this field line will always come back to where it started. So any field line that goes out always will have to come back in. So the end result is you don't have any magnetic charges that you can enclose. Gauss's law for magnetism is actually pretty straightforward. It says that the net flux through any closed surface has to be 0. And that's the way that it is, because there's no magnetic monopoles. So since you always have a closed loop. So there we have Gauss's law for magnetism. And so hopefully you can see there's a lot of similarities in thinking about magnetic flux, but we also have a couple of key differences with electric fields and electric flux. So let's see how I'm doing on time. Yeah, I think it would be useful if I took this time to just do also one quick example calculation here of magnetic flux. All right, let's do one example calculation. So we'll go ahead and create a little space. Actually, well, you know, I erased it now. Just quick write Gauss's law back down. We said it ended up being the integral of b dot dA equals 0. What I can do is I can actually just, you know, move my whiteboard a little bit here, all right, to create a little bit more space so that we can do one quick example calculation, all right? And so the example calculation I'd like to do is, let's imagine that we have a classroom or some room, and maybe let's think about, say, like one wall of the classroom. So we'll let this be the wall of a classroom, all right? Maybe I'll say it's the north wall of a classroom. And what we're interested in is, let's think about the Earth's magnetic field, all right? So let's say that Earth's magnetic field is angled 10 degrees from due north. So let's say that Earth's magnetic field comes through this window, right? And except it doesn't come straight through, maybe it comes through at a bit of an angle, right? It comes in at a bit of an angle, and that angle, we'll say, is 10 degrees. All right. Now, Earth's magnetic field, how strong is it? All right, the magnetic field of the Earth, it's about half a Gauss, 0.5 Gauss. All right, 0.5 Gauss. And let's say that this wall, you know, what's the typical size of a classroom wall? Well, maybe let's say that our classroom wall is 30 square meters. All right. So now we could think about, well, what's the flux through that wall? What's the magnetic flux through that wall? And to calculate that, well, we just use the formula that we have here. We say that the magnetic flux is the integral of b dot dA, all right, which in this case, that means it's going to be the integral of b dA cosine of the angle between them. Well, the angle between them here, that's going to be, let's plug in some values, all right? So we have the integral of b. B is half a Gauss, so if we put that in Tesla, that's 0.5 times 10 to the minus 4 Tesla, all right? And then we have cosine of 10 degrees. Cosine of 10 degrees, that's just a number. And then we still have dA, right? dA is just a little piece of that. But we notice these are both constants, so they can come outside the integral. So 0.5 times 10 to the minus 4 Tesla times cosine of 10 times the integral of dA. Well, in the integral of dA, that's just the area of the thing. So that's going to be 30 square meters, right? 30 square meters. And so we can then take, type all these numbers in a calculator, right? Multiply that all together, and that comes out to 9.8 times 10 to the minus 4. And you see that our unit here, right? The unit is going to be a Tesla times a meter squared, all right? And a Tesla meter squared gets a special name. So let's actually write that down here, all right? The unit is a Tesla meter squared, and that gets a special name. The special name of a Tesla meter squared is 1 Weber, all right? W-E-B-E-R, and it's abbreviated W-B. So 9.8 times 10 to the minus 4 Webers is the amount of magnetic flux. And it's just an amount. There's no direction for magnetic flux, right? It's just the amount that passes through. So we are finished when we've written that down. All right, so that is magnetic flux.